Hello viewers, today in this program I am going to explain you the multiple integral, double and triple integral particularly I am going to explain. To generate the double and triple integral, I am going to explain you the introduction of generation of double integration. Suppose f x y be a function of two independent variables x and y defined in some finite region R of a plane. Let us think of the region R as consisting of n numbers of elementary regions delta R1, delta R2, delta R3 and so on delta Rn. Let us suppose delta A1, delta A2, delta A3 and so on delta An be the respective area of these elementary regions and xr, yr be any point in the region delta R is 1, 2, 3 and up to n. If delta A1, delta A2 and so on delta An are sufficiently small, then f x y may be taken to be approximation of the function all over the elementary region delta R. Thus, f x1 y1 delta A1 plus f x2 y2 delta A2 plus f x3 y3 delta A3 plus and so on f xn yn delta an becomes summation of sigma r is equal to 1 to n f xr yr delta ar gives an approximate value of the sum of the values of the function at the points over the region R. If n the number of subdivision is increased indefinitely in such a way that each of the area delta A1, delta A2, delta A3 and so on delta An decreases to 0, then if this limit exists and defined to be the double integral of f x y over the region R and is usually written as integral over the R f x y dA. Thus, we get integral the double integral f x y dA is equal to limit n tend to infinity summation from R is equal to 0 to n f xr yr dA. Now, I am going to explain you the evolution of double integration using the procedure as follows. Evaluate the integral 0 to 2a second integral y square upon 4a 3a minus y over the integrand x square plus y square dx dy. Since here the internal limit is with respect to y, that is the x is function of y. So, we will integrate first with respect to x and then with respect to y as follows. Integral 0 to 2a integral y square upon 4a to 3a minus y over the integrand x square plus y square dx dy becomes integral 0 to 2a then x is cube upon 3 plus xy square from the limit y square by 4a to 3a minus y dy. On simplification, we find here the value of whole integral after performing the second integral with respect to x, we find 942 upon 105 a4 as the total value of the integral. The second example, I am going to explain you the evolution of double integral with the integrand x y multiplied by x plus y dx dy over the region bounded by the line y is equal to x and the parabola y is equal to x square. This example is differ from the first one. In the first one, the limits of integration are given, but here the limits of integration are not given directly, but region is given as bounded by y is equal to x and y is equal to x square. Here the region of integration is regular in both x and y direction as shown in the figure. First, we integrate the given function with respect to y and then with respect to x. The line y is equal to x and the parabola y is equal to x square meet the origin 0 0 and the point 1 1, and we note that it is from 0 to 1 for the x and x square is less than x. Therefore, the region bounded shown in the figure. Thus, the integral is from 0 to 1 from x square to x square y plus xy square dy then dx, that is equal to integral from 0 to 1 x square y square upon 2 plus xy cube upon 3 from x square to x dx, that is equal to 0 to 1 x 4 upon 2 plus x 4 upon 3 minus x 6 upon 2 plus x 7 upon 3 dx. So, we find x 5 upon 10 plus x 5 upon 15 minus x 7 upon 14 plus x 8 upon 24 from the limit 0 to 1. So, we find finally on simplification the value of the double integral is 3/56. Now, I am going to explain you the change of order of integration. Here in some cases we integrate with respect to y first and then with respect to x, but some integration are possible when we change the order of integration, that is we integrate with respect to x first and then with respect to y. The procedure is as follows. Consider the double integral f x y dx dy, where R is regular region. Assume that the region R lies between the lines x is equal to x naught, x is equal to x 1 parallel to y axis and y is equal to y naught, y is equal to y 1 parallel to x axis respectively. For points of R, the x coordinate lies in the interval x is equal to x naught to x is equal to x 1. Consider any x in the interval x naught to x 1 and keep the value constant. Y varies between psi 1 x and psi 2 x, where psi 1 x and psi 2 x are ordinates of the points at which the boundary of R is intersected by the line through x y and parallel to y axis. First integrate f x y with respect to y and then integrate the result with respect to x. Thus, the double integral f x y dx dy becomes integral from x naught to x 1, integral from psi 1 x to psi 2 x f x y dy then dx. Alternately, consider any y in the interval y naught to y 1 and keep the value constant. X varies between phi 1 y and phi 2 y, then the phi 1 y and phi 2 y are the abscissas of the points at which the boundary is intersected by the line through x y and parallel to x axis. First integrate f x y with respect to x and then integrate the result with respect to y to get double integral R f x y dx dy is equal to integral from y naught to y 1, then integral from phi 1 x to phi 2 x f x y dx then dy. For example, the change of order of integration in the integral from 0 to 1 and from x square to 2 minus x integrand here is xy dx dy and evaluate the integral. For the given integral, the region of integration is bounded by, here the limits are given as x is equal to 0, x is equal to 1, y is equal to x square, the parabola, and the line y is equal to 2 minus x. Thus, the region of integration OABC is as shown in the following figure. In the given form of the integral, we have to integrate first with respect to y and then with respect to x, so that the limits are followed. But on changing the order of integration, we first integrate the integrand with respect to x and then with respect to y. The integration with respect to x required the slipping of the strip up the region OABO into two parts, OACO and the triangle ABC. For the sub region OACO, the limit of integration are from x is equal to 0 to x is equal to root y, that is from line to parabola, and y is equal to 0 to y is equal to 1, that is line to line. Thus, the contribution of the integral I1 from the region OACO is I1 is equal to integral from 0 to 1, integral from 0 to root y, xy dx dy. For the sub-region ABC, the limit of integration are from x is equal to 0 to x is equal to 2 minus y, and y is equal to 1 to y is equal to 2. Thus, the contribution to I2 from the sub-region ABC is I2 is equal to from 1 to 2, then integration from 0 to 2 minus y, xy dx dy. Hence, on changing the order of integration, we get I is equal to I1 plus I2, that is equal to integral from 0 to 1, integral from 0 to root y, xy dx then dy, plus integral from 1 to 2, integral from 0 to 2 minus y, xy dx then dy. And for the evaluation of this result, we perform the integration with respect to x and then with respect to y as given in the picture, and finally on simplification of the integration we find the result as 3 by 8. Now, I am going to explain some another example for the change of order of integration. Here, change the order of integration and evaluate the integral as integral from 0 to infinity, integral from x to infinity, e to the power minus y upon y dy dx. Here, we cannot evaluate this integral as such, but if we change the order of integration, this integral is evaluatable easily. The region of integration is bounded by x is equal to 0, y is equal to x. The limits of x are from 0 to infinity, and those for y are from x to infinity. The region of integration is shown in the figure. On the changing the order of integration, we first integrate the integrand with respect to x and along the horizontal strip Rs, which extended from x is equal to 0 to x is equal to y, and then with respect to y, that is from 0 to infinity. To cover the region of integration, we integrate with respect to y from y is equal to 0 to infinity. Thus, the integral I becomes integral from 0 to infinity, integral from 0 to y e to the power minus y upon y dx dy, that is equal to integral from 0 to infinity e to the power minus y upon y x from limit 0 to y dy, that is on simplification becomes integral 0 to infinity e to the power minus y dy, that is equal to minus e to the power minus y from 0 to infinity, that is equal to minus 1 upon e to the power y from 0 to infinity, that is equal to minus of 0 minus y 1, that is equal to 1. Now I am explain you the triple integral and their evaluation. Let f is the function of three variable x, y and z. F x, y, z be a continuous function in the finite region V of R3. Divide the region V into n subregions of respective volumes delta V1, delta V2 and so on delta Vn. If xi, yi, zi be an arbitrary point of the ith sub-region, then limit n tend to infinity, delta V tend to 0, summation over I is equal to 1 to n f xi, yi, zi, dvi is represent the triple integral. If the limit exists, it is called triple integral of f x y z over the region V, and it is denoted as triple integral over V f x y z dv or triple integral over V f x y z dx dy dz. Evaluation of triple integral: if the region V is specified by the inequalities a less than equal to x less than equal to b, y less than equal to c less than equal to b, and z less than equal to e less than equal to f, and if a, b, c, d, e and f are constant, then the triple integral of the function f x y over the region bounded by the x from a to b, y from c to d, z from e to f is as follows. This is integral is equal to first integral from a to b, second from c to d, third from e to f. Integrand here is f x y z dx dy dz. We first integrate with respect to z, then with respect to y, then with respect to x to find the value of whole integral in triple integral form. For example, here evaluate the triple integral from 0 to a, 0 to a minus x, 0 to a minus x minus y, that is the region bounded by the tetrahedron from of the side a. Here the integrand is x square, so we integrate from 0 to a, 0 to a minus x, 0 to a minus x minus y, x square dx dy dz. First integrate with respect to z, then with respect to y, then with respect to x, and simplify the integration. We find the value of this triple integral is a 5 upon 60. Now I am going to explain you the change of variable in double and triple integral. Let R star be the domain in uv plane corresponding to domain R in xy plane. Then the double integral over the R f x y dx dy becomes integral over the region R star f u v Jacobian j du dv, where f u v is some function of phi x y and psi u v, and j is the Jacobian defined as partial derivative of u and v with respect to x and y in determinant form. So, the transformation j is equal to del x over del u, del x over del v, del y over del u and del y over del v in the determinant form. In many situations, transformation of double integral from Cartesian coordinates to polar coordinates is found to be useful. Therefore, we perform the change of variable of integration from Cartesian to polar as follows. The example here is: find the total mass of the solid bounded by the surface x square plus y square is equal to 9, z is equal to 1 and z is equal to 4. If the density is sigma x y z is equal to x square plus y square, the total mass of solid is given by mass is equal to integral from x is equal to minus 3 to 3, from y is equal to minus root 9 minus x square to root 9 minus x square, and z is from 1 to 4. Integrand here is sigma x y z dx dy dz. Here the limits represents the radius of circle, and then the y in the form of circle and z are constant. We convert the integral into cylindrical coordinate by transformation. X is equal to r cos theta, y is equal to r sin theta and z is equal to z. In cylindrical coordinates, the region occupied by the solid is described by the region r from 0 to 3, theta from 0 to 2 pi and z from 0 to 1 to 4. Also, f r theta z becomes sigma r cos theta, r sin theta and z, that is equal to r cos theta whole square plus r sin theta whole square plus z square. Hence, the mass is given by integral from r is equal to 0 to 3, integral from theta is equal to 0 to 2 pi, integral from z is equal to 1 to 4, r square multiplied by r dr d theta dz. We perform the integral with respect to z first, then with respect to theta, then with respect to r, and on simplification we find the value of the triple integral as twice of 243 pi by 2.
Yes, sir.
Now I explain you the change of variable in triple integral. Triple integral over f x y z dx dy dz is equal to triple integral over the volume v star f rho theta z rho d theta dz, that is the change of variable from Cartesian to cylindrical polar coordinates. Today in this program, I have explained about the multiple integral, particularly double and triple integral. Evolution of double integration have been explained with example. Change of order of integration have been explained in different application and different examples. Also, I have explained you the triple integral, evolution of triple integral and change of variable in triple integral. Hope you have enjoyed the lecture. Thanking you.